Can you guys see the slide? Let me know if you have any problem, with like the slide. Okay. I hope like yeah. Okay. Good. So let's continue. Okay. So this here I'm intended to introduce how the sampling is done. Okay, this is as I say, this is crucial to the development of Bayesian data analysis. Okay, so the set of algorithms that help sampling is called MCMC algorithms. Okay, so it is obviously the MCMC algorithm and the fast computer hardware that allowed us to do Bayesian data analysis. That's where you just hit the magic button for the inference. Okay, regardless how complicated your model may look like. Okay, with like the help of the hardware and this MCMC algorithm, you are able to to draw the posterior very easily. Okay, so actually, okay, this would this is not possible like just like 30 years ago. Okay, in other words, like the MCMC algorithm was like really developed like in the late 80s, early 90s. Okay, so in a long history of mathematics, the MCMC algorithms are really new. Okay, really new thing. Okay, but of course it has a long and lasting impact. Okay, so for realistic applications that neither have appropriate conjugate prior, nor can be solved using dense grid of points for prior distribution. Okay, MCMC method reduce the accurate approximations to Bayesian posterior distribution. Okay, produce. So it is able to efficiently generate the posterior distribution. Notice my word, efficiently. Okay, because obviously if you use grid points, you can always generate the prior distribution. It's just like remember like if your model contains like tens or even 20 or even more than 10 variables, independent variables, then grid points, okay, even if you only have like a 10 point per dimension, it's going to grow, exceed the computer's computing power. Okay, so so how do we do it? So there are some assumptions that we have to have for any MCMC algorithm. Okay, the first one is the prior distribution is specified by a function that's easily evaluated. Okay, which is normally the case. Okay, we always specify the prior. Okay, and the prior is normally obtained from a very simple, probability distribution, okay, which can easily be evaluated, okay. So if you specify a value for theta, okay, P of theta can easily be determined, okay. So value of the likelihood function P of D on condition of theta can also be computed for any specified value of D and theta. So this is your likelihood function, okay. As I said, I mean, the likelihood function is one part of your model, okay, which has to be defined, okay, okay, and the definition has to be in a form such that it can be evaluated easily once the data and the theta are given. I mean, keep in mind that I mean, P of D is difficult to evaluate, but P of D on condition of theta, okay, this likelihood in most cases are very easy to evaluate, okay. For example, like if you flip a coin, okay, say the theta is 0.5, and the probability of coming up like 3 straight heads, well, this probably can be easily calculated, right? So this type of stuff, these two assumptions are very important. So we call this algorithm MCMC, right? So what is MCMC? Okay, the first MC stands for Monte Carlo. Did I explain the meaning Monte Carlo to you guys? Monte Carlo is the most famous gambling city in Europe. Okay, it's I believe it's in somewhere in France. Okay, and just like Las Vegas. Okay, because nowadays like people, when we talk about gambling, we say it's Las Vegas or like Macau, but in the old days, okay, when US is still not, when US is still, what should I say? I should say when Europe is still the dominating power in the world. Okay, I'm not talking about like very, long time ago. I'm just talking about like about maybe before the World War II. Okay, so like about, well, that was 1940, right? So about like 80 years ago. Okay, 80 years ago. Okay, the world order is totally different, okay, from now. Okay, I mean, so people, okay, all the research work were published either in Germany or in French. Okay, so people tend to learn the language people learn are, the language in Europe. Okay, and because of that, okay, a lot of terms used in the finding will be, will have something to do with the Europe. Okay, so for example, this Monte Carlo. Okay, Monte Carlo refer to pretty much just a random process, because Monte Carlo, as I say, is the biggest gambling city in Europe. okay, or I probably should say like it's biggest gambling city in the world, okay, back to the old days, okay. So that is why, okay, people called random prop, because in gambling place, I mean, you throw a dice, you do some, any gambling pretty much is about random event, right? So I mean, so we naturally named like a random process after Monte Carlo. Okay, so um, here we want to approximate distribution with a large amount of sample. Okay, the fundamental is this concept of representing distribution by a large representative sample, such as pool and surveys. Okay, but random is subset. Simply a subset of people from population. We want to estimate the underlying tendencies in the entire population. Okay, so we do this all the time, right? Like before the election, we do a poll to see like who is winning, right? Which candidate is winning? Okay, so for this type of like survey or pool, okay, the larger the population, the better the estimation, obviously. Okay, so the population from which we are sampling, okay, is defined as a distribution, okay, mathematically, okay, such as posterior probability distribution, okay. So we want to sample from posterior probability distribution, okay. So example to show you, okay, you can see, okay, this is a distribution, okay, on the upper left corner, this is distribution. If you use like 500 samples to simulate it, you will see it is not very smooth, right? Not very smooth. It has like edges, like all over places. Okay, and you get the mode to be 0.723. I mean, compared to the 0.7 mode in the theoretical value. Okay, this is obviously this approximation is obviously not good. That's because we only have 500 samples. But when you increase the sample to, for example, 5,000, you see the distribution becomes much smoother, and the mode becomes much closer to the 0.7, right? And you could increase this 5,000 to 50,000. Okay, once I mean you increase the scale of your sample, okay, by another order. And obviously here you can see the distribution is very smooth to say the least. And the mode, okay, is getting even closer to the real one. This is actually a very good approximation already. Actually, I probably should say like, even with the 5,000 samples, the result is already pretty much, it's already very close to the real distribution, okay? Because you see the difference between 7 and 0.696 is only 0.004, right? So it's less than 5%. Well, probably a little bit more than that 5%, maybe 7-8%. Okay, but you get an idea. This is all these are, as long as you increase the sample size, okay, the approximation can be done very well, okay? So that's the idea of like using the sampling technique to approximate a distribution, okay? But obviously, like when you have so many variables, that means like your distribution, is your random variable, okay? Sorry, independent variable. The dimension is so huge, and the combined space of your independent variable is so huge. How can we sample a large number of representative values from a distribution with such a large space? Okay, as I said, like a grid point approach doesn't, it's not effective enough, right? So we can ask such a question to a politician. Okay, what do we mean? Okay, let's suppose, okay, an elected politician, okay, lives on a long chain of islands. Okay, we assume his territory is a long chain of islands. Okay, so he is constantly traveling from island to island. Okay, because he's a candidate for the next election, right? So he wants to stay in the public eye. Okay, he wants everybody to see him, to know who he is, so that like in the next voting, he can get more number of votes, right? Okay. So at the end of a grueling day of photo opportunities and fundraising, okay, oh, by the way, in US, okay, the campaign is always about photo opportunity, photo taking, and the fundraising. Okay, it's very different from Taiwan. In Taiwan, like you see, like candidates just go everywhere to shake hands, right? Shake hands. But in US, you don't see that very often. Okay, so basically just like a photo taking and fundraising. If you support a certain candidate, you donate to that candidate. Okay. So anyway, so this petition has to decide, okay, a few things at the end of the grueling day. Okay. First, stay on the current island. Okay. Obviously, this petition must be on one of the island at this moment, right? So he needs to decide whether or not to stay here. Okay. If not, he has two choices. One is move to the adjacent island to the west, or move to the adjacent island to the east, right? So, well, we only have this, let's assume we only have these three options. Okay? So, what is our goal? Our goal is to visit all the islands proportionally to their relative population. Okay, so that the politician spends more time on the more populated islands and less time on the less populated island. Okay, because after all, the politician only has limited amount of time, right? So if he wants to allocate his time to different islands, okay, the island with more population obviously has a chance to get more votes, right? So he should stay there longer, okay, compared with like the islands with less population, okay? There are a few assumptions, okay, that we have to go through, okay? First, the politician has no idea what the total population of the island chain is, okay? He doesn't know the whole total population of his country. Assume he doesn't know that. Second, the politician doesn't even know exactly how many islands there are. Okay, well, you can say this politician is lazy. Okay, he doesn't even know like how many islands we have on this, in this nation. Of course, this is a made up example. Okay, this is a made up example. But let's assume, okay, this is the case. Okay, and the third one, the politician can ask the mayor of the island. Okay, assuming each island has a mayor. Okay, or a chief, whatever you want to call it. Okay, so he can ask the mayor of the island they are on. How many people are on the island? Okay, he can ask like how many people on the island that he's currently located. And also, when the politician proposes to visit an adjacent island, say to the island on the left, okay, he can ask the mayor of that adjacent island, how many people are on that island? So if the politician proposed to move to the left, he first asked the mayor on the island to the left, okay, how many people are on that island, and then decide whether or not to move to that island. Okay, so this is only these 5 assumptions. To be honest, like the politician really doesn't have a lot of information, right? He doesn't know the total population. He doesn't even know the number of islands, right? So how do we deal with this? Well, it's 10:54. So let's take a 10 minutes break. When we come back, okay, we will continue on this NCMC chapter. Okay, let's get started. Yeah. So we just talked about this um, fake example, right? I mean, it has a chain of islands, and we don't know like the total population. And for each island, if you are on the island, you can ask the population of the island. And if you decide to move to not decide, if you propose to move to one side of the island, you can ask like the population on that on the island you propose to move to. Note that this is proposed. Okay, this is proposal. This doesn't mean the politician will move to that island. This is just a proposal. Okay, I mean depending on the population of that adjacent island, the politician will then make decision. Okay, so this is a heuristic. This heuristic is very simple, but interestingly, it works. It works wonder. Okay. So first, this politician flips a fair coin to decide whether or not to propose the adjacent island to the east or adjacent island to the west. So one side represents the east, one side represents the west. Okay. If the proposed island has a larger population than the current island, then the politician definitely goes to the proposed island. So for example, like after he flipped the coin, if it's the left, and the left island has more population than the current one, then the politician will go for sure. Okay. However, if the proposed island has a smaller population than the current island, then this politician goes to that proposed island only probabilistically. Okay, what do we mean by probabilistically? Okay, it means that the politician will go there. Okay, you know, you know, proportional. Okay, the proposed island has a population as big as the current. How should I say? For example, okay, if the proposed island has a half of the population than the current island, then the probability of going there is 50%. If the population of the proposed island is 30% as the current island, then probability is going to be 30%, something like this. So if say like okay, this 30% or 50%, okay, if it turns out that I mean, well, the politician doesn't move, then he will stay on the current island and do this process all over again. Okay, for every day. Okay, every day. Well, I probably should say like at the end of every day, the politician do this, you know, decision making to see like where to move to. Okay, for the next day. Okay. So that's like try to make the last step of the heuristic to be more mathematic. Okay, let's put it as a as an equation, as a formula. Let's denote the population of the proposed island as P proposed and population of the current island as P current. So the petition only moved to the last popular island with the probability P move equal to P proposed divided by P current. So the partition does this by spinning a fair spinner mark on the circumference with uniform value from 0 to 1. I mean, this can be done like by a simple computer program very easily, right? So if the pointed to value is between 0 and the P move, then the partition move. I mean, we can do better. We can just write a program to generate a value randomly between 0 to 1. Okay, that's probably faster. Okay. Anyway, you get the idea. So let's because like in reality, we want to see like the impact of this approach. So that's intentionally let's assume the number of islands is 7 in a chain. Okay, with relative populations. Okay, proportional to the number of islands. Okay, the first island, we have 7 islands, right? So let's number these islands from 1 to 7. 1, 2, 3, 4, 5 to 7. And let's assume the first island, say, has like a 100 population. The second island has 200 population. The island 3 has 300, and so on. So the ratio is 1 to 2 to 3 to 4 to 5 to 6 to 7. Okay, just like exactly match like the number on the island. Okay, this is obviously just an example. Just an example. Okay, I mean. So P parenthesis refers to a relative population of the island, just a ratio. That's good enough because I mean, we will decide to move or not based on the ratio, right? So this is not the absolute population and not its probability mass, okay? So let's see this figure. Okay, the lower figure, okay, the lowest figure represent like a 7 island and their relative population. Okay, the first island has a population of 1, second island has a population of 2, third island has a population of 3, and so on to the 7th island has a population of 7. Okay, so now let's assume the partition start from the 4th island, the middle one. And then, okay, on the first day, the partition happens to start from the middle island, okay? And to decide where to go on the second day, you flip the coin to propose moving, okay? And in this case, the coin proposed moving right. Okay, moving right. And the island on the right-hand side has more population, right? So he definitely moved here. Okay. And then the next day, okay, the second day, okay. When t is 2 and theta is 5, I mean, theta means like where this partition is located. The coin flip proposed move to the left, okay? And the probability of accepting this proposal is, well, because like and probability move to the left, no, 0.8. Obviously, after this probability, like we decide to stay in fifth island for one more day. You can see we stay here longer, right? And then the third, again, we flip the coin, decide move left or move right. Now, again, we move to the left. I mean, we propose to move to the left. And with the same probability, like 4/5. And then, this time we really move to the fourth island, okay, and so on. So this shows the trajectory of the partition. And then, okay, if you accumulate the number of stay on each island, okay, for a long period of time, something interesting happens. You will see that the partition eventually stay on each island, okay, proportional to the population, the relative population of each island, right? So this, this random process, okay, even though it's we use a heuristic to decide move left or move right, okay, but eventually we are able to get more samples from the more populated place, which is the seventh island, and the fewer sample from the less populated island, which is like, for example, the first island, naturally, right? But you may argue, wait, this is just one special case, right? This is maybe just one special case. It turns out that this is always going to be the case. Not only that, okay, you may argue, well, maybe the starting point plays an important role in here, okay, because we start from the middle, right? The answer is no. No matter where you start, okay, you just are going to create such a result regardlessly where you initially you get started. So that's of course I promise you that I mean we will explain the sampling technique, okay, but at the same time I know that we are not going to really like do this like a math department, okay. So here, okay, a compromise that I'm going to do is that, okay, I'm going to show you a few arguments to convince you that this is indeed the case, okay. So how do we do it? Okay. I'm going to do two different approaches. Okay. The first one is this. Okay. This figure show you the probability that a politician is located at the island at a certain day. Okay. We know at the day one, on the day one, politician is on the fourth island, right? So the probability for the politician on the fourth island is 100%, right? And the probability for the politician on the other islands will all be 0, right? Okay. So when T is 2 on the second day, what is the probability that the politician is located? Okay. We know like at the end of the first day, politician can flip a coin to decide move left or move right, right? If he decides to move right, because the right hand side, the island on the right hand side has more population, right? So he will definitely go, right? So it's going to be, because the coin flip is 50% to the right, right? So we have 0.5, okay, to that position on the second days on the fifth island. Another possibility is that another 50%, the position flip the coin and the result is to move to the left, okay? And the chance for this, the chance for the partition to really move to the left is 0.5 times 3/4, right? Because that's the ratio of the population, right? So the result is like, zero, no, so it's a 3 divided by 8. Well, so it's going to be somewhere near 0.4, but not exactly. I think it's 0.375 if I remember correctly, right? So there's also a chance that the politician will stay on the island 4, which is 0.5 minus 0.375, okay? And it's going to be like a little bit more than 0.1. Okay, so this is the probability where the prediction will be on the day 2. Oops, sorry. And obviously, you can keep doing that, right? This is a very simple way to calculate this probability. Okay, start from the 5th island. You have like you can either move to the right or move to the left. You compute all the possibility, and from the 4th island again, you can move. The partition can move to the left or move to the right. You do all these calculations, and they add them up. So at the end of the 3rd day, the probability for partition to stay on different islands looks like this. This is the 5th day. This is 3rd day, and end of 3rd day. This is end of 4th day, end of 5th day, end of 6th day, and so on. Okay, if you use obviously, I mean, the first 2-3 days you can calculate by hand. If you want to do it like for a longer period of time, okay, you obviously should write a program. So you can see when T is like 12, 13, it already gives you a very good indication that it is proportional to the relative population of each island, right? But it's still not so smooth yet. If T is 99, okay, you can see it is going to be an almost exact match to a target. So this, again, let me remind you, this indicates the probability that this partition is at each island. And this happen to be proportional to the, the relative population at each island, right? So this is a very interesting observation, okay? And this obviously this is just one argument, but this is not exact proof, okay? Yeah, I think I already explained this, but so that current percent be theta current will propose to move one position right or one position left. The specific proposal is determined by flipping a coin. So probability is 50% head, 50% tail. So this range of possible proposed moves, okay, all the possible proposed move, okay, and the probability of proposing each, okay, combined is called proposal distribution. There's a, special terminology to call this. Okay, in the present algorithm, the proposal distribution is very simple because you can only move to the left adjacent island or move to the right adjacent island, each with a probability 50%. Okay. So we can also try to, write our formula a little bit better to be something like the following. Okay, P move will be mean of, P theta proposed divided by P theta current. This P indicates the relative population, okay, or 1. What do we mean by here? Okay, because we sort of like combine moving to the left and moving to the right into one single equation. Because if you move to the right, because you have more population on the right, I mean, for the island on the right, right? So you will definitely move there, right? But instead of just using a, if else, we just, use this one. Okay, because like, if you put like a P theta proposed, okay, and P theta current, okay, I mean, if you propose to move to the right, okay, because the P theta proposed is larger than P theta current. So this, fraction is going to end up with a value higher than 1, right? But we know like the P move cannot, because this is a probability, right? So it cannot be higher than 1. So we just, make sure it is, upper bounded by 1. That's it. That's it. So this is actually a random walk process. Okay, random walk process. Okay, so remember I told you like this chapter is called MCMC. I mean, one MC stands for Monte Carlo. Another MC stands for like a Markov chain. Okay. What is Markov chain process? Okay. If whatever you are, I mean, this process will only be dependent to the previous status. Okay. If the next move, next status is only dependent to the previous status, just the previous status, okay? Not the previous status, okay? Just like the previous status. And this process is called like, Markov chain, okay? And by the way, random walk is a Markov chain process. Okay, why? Because like the place you move to obviously is determined by your previous location. Okay, for example, like you are on the island 4. The only places you can go are island 3, island 5, and island 4, right? Because, well, those are either the adjacent islands or where you are located right now, right? I mean, you cannot move directly from island 4 to, for example, island 1. That's just not possible, right? So, so this is that's why this random walk. This is a Markov chain process. Okay, and for a random walk process, okay, to happen, we must have these 3 requirement. Okay, requirement. They are pretty straightforward actually. Okay, we just try to list them so that make it obvious. Okay, so first we must be able to generate a random value from the proposal distribution to create P proposed. Okay, in this example that we are talking about is that we must be able to flip the coin. Okay, I mean, of course, like in a later part, I'm going to tell you that this proposal distribution, can be more complicated. For example, it could be Gaussian. Okay, it could be uniform, by the way. But regardlessly, okay, you can always sample from Gaussian or sample from uniform distribution, right? So to sample from a given distribution is normally never a problem. Okay, so this is the first must. The second must is we must be able to generate a random value from a uniform distribution to accept or reject the proposal according to P move. Again, this is pretty straightforward. Okay, pretty straightforward. Not much that we can talk about. The third one is we must be able to generate a random value. Sorry, that's the third one. The second one is we must be able to evaluate the target distribution at any proposed position. Okay, in other words, in this example is we want to compute P theta proposed divided by P theta current. This couldn't be any easier, right? For this current example, but of course, I mean, in the later part, okay, that we are going to use this one to do the sampling, then yeah, I mean, it's normally not an issue to to evaluate the target distribution at any proposed position. Okay, this is normally never an issue. Okay, so so by being able to do these three things, okay, we are able to indirectly generate random samples from the target distribution, and this random walk technique is very, very useful when the target distribution P of theta is a posterior proportional to P D on condition of theta times P theta. Okay, we know this P theta equal this equation, right? So merely evaluating P D on condition of theta times P theta without normalizing it by P theta, P of D, okay, we don't really need to normalize it, okay, as long as we can make sure that we are generating sample that are proportional to this, you know, P of D on condition of theta times P theta, okay, or the posterior, then it's good enough. So I just told you, okay, here, okay, I will not give a formal proof, but I'm going to give two arguments, right? That why the MCMC works, okay? The first argument I gave you is this one, right? And but that one is not so strong, okay? But at least it's a circumstantial evidence, okay, to show you like you know why this approach works, okay. But now I'm going to tell you another argument, okay, and this argument combined with the previous one should give us a relatively good proof, okay, not necessarily formal either, because again, we are still considering a special case, okay, but the you know, the basic idea will be the same, okay. So let's consider two adjacent positions and the probabilities of moving from one to the other, okay. So see the relative transition probabilities between adjacent positions exactly match the relative value of the target distribution. So we can extrapolate, okay, this result across all positions. And, you know, in the long run, each position will be visited proportionally to its target value, okay. So how do we do it? Okay, it's like this. Suppose we are at position theta. The probability of moving to theta plus 1 is denoted by P of theta to theta plus 1. It's the probability of proposing that move times the probability of accepting this move, okay, if proposed, okay. So which is like, you know, P of theta to theta plus 1 is 0.5 times this one, right? This mean of P theta plus 1 divided by P theta 1. We know this from this Barton equation, right? So if we are presently at position theta plus 1, the probability of moving to theta, okay, is going to be represented by this one, right? P of theta plus 1 going to theta is 0.5 times this one. So if we try to see, okay, there are two possibilities. One is, you know, you try to, you know, calculate the ratio, and one, you know, of course, because one population must be larger than the other, right? Either P of theta is larger than P of theta plus 1, or P of theta plus 1, or P of theta is smaller than P of theta plus 1. So if P of theta plus 1 larger than P theta, you put this, okay, then this one will become 1, right? The mean of this one becomes 1. And you only have this one remains. And this one will remain. So it becomes like this. And if P theta plus 1 is smaller than P theta, then this one remains. P theta plus 1 divided by P theta. And the lower one becomes 1. So it becomes this. Okay. And no matter which option you have, you're always going to end up with P theta plus 1 divided by P theta. Right? And then you can, you know, so every adjacent position, the ratio shows something like this. Okay, so eventually, that's why, okay, you end up, the frequency will match with the population, will be proportional to the population of each island. Okay, and you could, okay, to be more specific, you can put the whole thing into a transitional matrix. Okay, so for each row, for each column, okay, represent okay, where the probability that I mean, some, how should I say? I should say for each row represent from P theta to P theta minus 1, okay, or from P theta to P theta, or from P theta to theta plus 1. Okay, you can write it like this. Okay, so then, okay, if you try to put the formula that we use in this example into this matrix, it will look something like this. And then, okay, you could use this one to calculate you know, to obtain this one actually. Okay, initially, okay, when the partition is at the theta equal to 4, it means you know, originally, I mean, we can represent the probability that the partition is at each item as a probability vector. And initially, because he was on item 4, so it's going to, the vector is going to look like a 0, 0, 0, 1, 0, 0, 0. Okay, and if you multiply that vector, okay, to this equation, this matrix, it's going to give you the second day. Okay, I mean, where this partition is going to end up with on the second day. It's going to give you this one. In the vector form, in a vector format. And then you can apply the matrix to this vector again, and then you will get this. And you multiply matrix to a set to the vector this one, you'll get this one, and so on. So eventually, okay, you can use that transitional matrix to compute like to obtain this result. Okay, I mean, no matter where the initial point is actually. So so this is, you just formulate it as a row vector. W is a location probability into a row vector W, and then you use W multiplied by the matrix, okay, and you get like the next probability, location probabilities. So so determine the probability of the location at the next time is going to be like a W times TRC. Okay, so I already talked about this. Okay, so repeating this process will generate the graphs in slide number 16. Okay, I already told you that. So here's the interesting part. Okay, when the vector of precision probability is the target distribution, it stays that way on the next time step. Okay, so in other words, like this transition will make sure your probability distribution, the location probability vector, keep diffusing until it will stabilize. Okay, when the target, when it reach like the target precision probability that's match with the target distribution. Okay, so this is like the most important point. Okay, so yeah, I guess it's this is difficult. I mean, without going to the without using the whiteboard, it's difficult for me to show you why this is the case. Yeah, but I think we are really running out of time anyway today. So I will complete this proof next time, okay, in class. Okay, basically like okay, this one indicate like okay, you know, in the next step, you know, how this probability distribution is going to end up like. But I'm going to show you, okay, it's going to, you know, it's going to stabilize if it match with the target distribution. Okay, there are 4 cases to discuss, okay, to be exact. So in the class, I will try to discuss at least 2, okay, and then you can do the other 2 by yourself, okay? Yeah, I guess like, yeah, unfortunately, I mean, it's just very difficult to, even if I use whiteboard, I mean, to type those formulas like by hand is going to take too much time. So I give up. I think like it's about time that, I mean, we it's that, I mean, that it's already 11:50. So I think like we will stop today's lecture here, and I'll try to finish up this discussion next time. Okay. Yeah. So yeah, thank you ever. For coming to the class. I will see you guys. I really hope I will see you guys. In person next week. Okay. Thank you very much. Okay. Bye.
So let's get started. Okay. First, apologize for the for switching to online classes like last 2 weeks because of my COVID-19, and yeah, I think I'm fully recovered now. So we will switch to this regular class mode, hopefully till end of the semester. Okay. I still have a little bit issue with my throat, even though the test kit shows only, test kit only show negative, but my voice is not fully, back to normal yet. So if you feel that my voice is a little bit low, okay, and you couldn't hear it clearly, you can always ask me to repeat, okay? And yeah, the first thing is the homework 3, right? The due date of homework 3 is around the corner. Is that right? Yeah, just want to remind you, okay? Yeah, and when you submit to the homework 3, okay, remember to turn in your term project lab members as well, okay? Because I believe I said each group to have 3 students, okay? So if you really couldn't find your teammates, the TA will randomly assign teammates for you, but I really don't suggest you do it this way, because from the past experience, the randomly assigned teammates normally do not do much work, okay? So which will obviously hurt your term project performance, okay? So don't try to get your teammate, okay, as quickly as possible, okay? So so last time, okay, we were talking about the sampling technique, okay? This is a crucial technique that was proposed in the late 1980s and early 1990s, okay? Before this, random sampling technique was proposed, actually, the Bayesian inference wasn't possible because, as I said, even though you can use grid approach, okay, if you cannot use grid, if you want to use a conjugate prior, the situation is the conjugate prior is limited in very few likelihood cases, okay, and also the conjugate prior itself has only limited shape, okay, which doesn't simulate a certain prior very well, okay. If you want to do the approximation, meaning you want to use a grid point to approximate the posterior, okay, In real application, I mean, most likely you end up having like a high dimensional space. Okay, when I say high dimensional, I'm talking about like more than 10 or even 20 parameters. So consider if you try to sample 10, just 10 points from each dimension. If you have like say like 20 dimensions, it will be 10 to the power of 20. Okay, that's just impossible. Okay, just impossible. So this metropolis sampling, okay, that we talked about last time, okay, is able to approximate the posterior, okay, or let me just not to use like any particular because there are only limited assumptions for this random walk. Okay, this one. As long as we are able to evaluate the target distribution at any proposed position, okay. In other words, like the current probability density, okay, versus the target, like the proposed locations, like probability density. I mean, here, I mean, we don't really need the real value. We only need like the ratio. This is very important. Okay, we only need the ratio. Okay, and then we need to, the first one, when you generate random value from proposed distribution, okay, and the second one, I mean, I just say that, and the third, we must be able to generate a random value from uniform distribution to determine whether or not to accept the proposal or not. Okay, so these three steps, okay, if you repeatedly do that, okay, you will be able to generate samples very effectively. You don't really need like you just need like for our purpose, to generate the posterior, okay, distribution, we can use the P of D on condition of theta times P of theta, okay. In other words, like this is likelihood. This is like prior. The prior multiplied by the likelihood. Normally, okay, in order to get the posterior, you need to divide this term by P of D. But the P of D, the denominator, is the issue, right? Is the issue that we have to do in integral to get the P of D. But okay, because for this particular sampling technique, you can see that because P of D is the same regardless of the location of the theta. So the denominator cancel out each other, okay, in this formula. So you don't need to compute P of D, okay. So this is very, very important. We can just apply this sampling technique repeatedly to generate the posterior samples like very effectively without the need of computing the difficult part of the posterior formula. Okay, so So I try to show you that this idea, okay, this idea work, okay, in the sense that it's going to, allow the result to converge, okay, to the desired property. We use this, if you try to, see the ratio between from the probability from theta to theta plus 1 divided by probability of theta plus 1 to theta, it turns out to be this one, okay? And if you try to, extrapolate this result, pretty much you are going to end up with like the desired, okay, distribution that we are looking for, okay? And we can also write it into a matrix format, and if you, really, put the example that we have in this matrix, it looks like this, and then you can just try to represent the current location, the probability of the current location as a vector, and then you just multiply that vector with this matrix. You are going to end up with like the probability of each location, okay, in the next step. So pretty much you just keep multiplying this matrix, and you are going to end up with like something like this. Okay, suppose you start from like 0, 0, 0, 1, 0, 0, 0. Okay, because the initial location of the that partition is in the fourth island. So initially, okay, the probability will be 0, 0, 0, 1, 0, 0, 0, because he is in the fourth island and not in any of the other island. Okay, and you apply, you multiply this vector to that matrix. Okay, you are going to get this. You multiply this one with the matrix again, you get this one, and so on. Okay, so this matrix sort of explains, okay, how we obtain that this result, okay, this result. But we can also look at this in a different way, okay, in the sense that first, you can clearly see that, okay, no matter where you start, okay, you could start from the fourth island, you could start from the first island, okay, you can start from any location, okay, you will see the probability at each island naturally diffused, okay, to different islands. So that's the first thing. You can derive, okay, no matter where you start, okay, you can give it a try, okay, you can put like maybe 1, 0, 0, 0, 0, 0, I mean, put the partition at in the first island first, or the second island, or the third island, and so on, okay, no matter where you put that partition initially, okay, the probability that he will be at each island will naturally diffuse, okay, to different islands. Okay, so this is the first thing. And the second thing is, let's look at this formula. Okay, so we just try to multiply the current distribution with the this matrix, because this matrix you can see it only has, for each location it only has, if it's like a row vector multiplied by this matrix, you understand that it's going to end up with like for each location, it's going to end up with only 3 terms, because only 3 terms are non-zero, okay, for each column anyway. So if you try to write it out, it's going to become something like this. Okay, for the rth term, it looks like this. Okay, then, okay, we can also break this thing into 4 cases. This is where I end up with, like at the end of the last lecture. Okay, because it, without, writing on the whiteboard, it's just difficult for me to explain. Okay, so first, you may ask, we need to discuss this in 4 different cases, but the first thing you want to ask is, what 4 cases? Shoot. Let me. Okay. So, we know in these terms, okay, they are influenced by, the P of theta minus 1, and the P of theta plus 1, right? So we have 3 we have these 3 terms, and their relative relations will, impact this equation, right? Okay, in other words, which one of them is bigger? Which one of them is bigger? Okay, so if you consider all their relations, okay, there are 4 cases. You may wonder, why do I say 4 cases? If you try to, sort all these 3 terms, you should get the factorial of 3, right? 6 different cases. Okay, so why do I say 4 cases? It is because, okay, we only care the relation between these 2 and the relation between these 2. The relation between these 2, okay, one of them is larger, the other one is smaller. And the relation of these 2, one of them is larger, the other one is smaller. Okay, because there's no term. Here you can see we have this term, we have this term, we have this term, we have this term. And we do need to find out which term is larger and which term is smaller. Okay, for between P theta minus 1 to P theta, and between P theta to P theta plus 1. But we never need to care, the relation between P theta minus 1 and P theta plus 1. Right? Here it's about P theta minus 1 to P theta. This one is between P theta minus 1 to P theta. This one is about P theta to P theta plus 1. This is about P theta to P theta plus 1. No term, okay, here, need to ask the relation between p theta minus 1 and p theta plus 1, right? So you have two cases here. You have two cases here. So 2 times 2 is going to be 4. Okay, it's going to be 4. Okay. To be exact, let me list all the possible cases that we want to discuss. Okay. The first case, p of theta minus 1 is smaller than p of theta. And then p of theta it happened to be smaller than p of theta plus 1. Of course, in this case, it implies that p theta minus 1 is also smaller than p theta plus 1. Okay, it happens, okay, to be this case. So this is the first case. The second case, p of theta minus 1 is smaller than p of theta. But, okay, p of theta is larger than p of theta plus 1. Okay, in this case, you know, obviously, we know p theta is the biggest term, but we don't know the relationship between the p theta minus 1 and the p theta plus 1. But that's okay. That's okay. It's good enough. Okay. The third one is p theta minus 1 is larger than p theta. And it happened, p theta is also larger than p theta plus 1. Okay, the fourth one, the fourth case is p theta minus 1 larger than p theta. But, okay, here we have p theta, smaller than p of theta plus 1. Okay, so in the fourth case, we know p of theta is smallest among 3. But we don't know the relationship between p theta minus 1 and p theta plus 1. Which one is bigger? We don't know. But so these are the 4 cases that we want to discuss. Okay? So obviously, I mean, you can think, okay, for the case 2 and the case 3, if you want to get a total order, I mean, in other words, if you want to know the relationship between p theta minus 1 and p theta plus 1, then you can branch each of the case 2 and the case 4, okay, into another 2 cases. But since in our formula, we don't need that, okay, so we are satisfied with these 4 cases, okay? And so let's, obviously you can see that, okay, the case 1 and the case 3 are similar, okay, in the sense that there's a total order, right? And the case 2 and the case 4 are also similar in some sense because like the case 2, p theta is the largest, and the case 4, p theta is the smallest, right? So let's just, instead of like going through all 4 cases, let's just focus on 2 of them, okay? You can, let's just pick like the first case and the second case. The third case and the fourth case, you can do it by yourself, okay? So let's try to plug in the first case and the second case into the formula and see what this formula is going to end up with, okay? So the first case, we know p theta minus 1 is smaller than p theta, and it's smaller than p theta plus 1, okay? So this multiplication Okay, that's the first term. Which one is going to, are we going to have? Because p theta minus 1 is going to be smaller than p theta, right? So this is going to be larger than 1, right? Because the smaller one, the smaller term, happen to be in the denominator, right? A nominator, I'm sorry. The smaller term happen to be in the nominator, okay? So this term, okay, end up going to be larger than 1. But we are going to find, we want to take the smaller one of this term and the 1, right? So this term becomes 1. So the first term will become p theta minus 1. Okay, this one, right? Oh, sorry, there's a z. Okay, there's a z. Let me just put like this. Right? This is the first term. This part become 1. Okay? And then plus p of theta divided by z times, okay, inside the parentheses we have this. Okay? So p of theta divided by z. Okay? And inside the parentheses, we actually have 2 terms. So the first term, okay, well, we know p of theta is larger than p of theta minus 1, right? So this term end up is going to be smaller than 1. So we have 1 minus this fraction. So it's going to be 0.5 times p theta and p theta minus 1. Right? Plus 0.5 times okay. Oh, sorry. It should be 1 minus. Okay. So we have a larger plus 0.5 times inside here 1 minus okay, and the p theta and the p theta plus 1. We know p theta plus 1 is larger than p theta, right? So this is going to be larger than 1. This is going to be larger than 1. So, well, we are going to take 1 from here, right? So 1 minus 1, this term becomes 0, right? So 1 minus 1. So this term cancel out. Okay? And then plus p theta plus 1 divided by z, okay, times 0.5 0.5 times here, okay, p theta and the p theta plus 1. We know p theta plus 1 is bigger, right, in the first case. So this term is going to be smaller than 1. So we are going to take this, so it's going to be so okay. So that's like, try to simplify this a little bit. Okay. We know all these, first, I mean, these two cancel out, obviously. Okay. And if you multiply this p theta into this parentheses, okay, this one, it becomes p theta minus p theta prime. P theta minus p theta minus 1, right? Okay, so that's, because everyone has a z as denominator, and 0.5, okay, there. So, okay, once you get these two out of the equation, the first one has a p theta minus 1, okay? And the second one, you get this one out, you get this one out. You are going to have like a plus p theta, okay, minus p theta minus 1. And then you get this one out, you get this one out. And then you have plus p theta, right? So, well, then you can see that, okay, we actually add 2p theta. We also add 2p, these two cancel out. Okay, so it's going to be z is going to give you this term, right? Okay, so the other one, the second case, okay, the second case, I mean, do you mind I erase this? Okay, should be very easy, right? The second case is that, okay, your p theta is the largest, one. I mean, both p theta minus 1 and the p theta plus 1 are smaller than p theta. Okay, so we can plug in this into this formula, okay, and again, you can see, because p theta is larger than p theta minus 1, so this term becomes larger than 1. So we will only take 1 here. So it's going to be p theta minus 1, 0.5 times z, theta plus 1. Oh, sorry, minus 1. And then plus p theta divided by z and times the here, okay, 0.5 times 1 minus, okay, and we know p theta is the largest term, so we know this one is going to give us a smaller than 1 value, so we are going to take this, okay, so p theta minus 1, right? So we are going to take this. And then, okay, plus, again, this one is going to be a value smaller than 1. So we are going to take this one again as well. So plus 0.5 times 1 minus p theta plus 1. Okay, and then, okay, the last term, okay, plus p theta plus 1 divided by z times 0.5 times this one, okay, again, because p theta is larger than p theta plus 1, so this term is going to end up with to be larger than 1, so we are going to take 1, so just 1. Okay, so let's try to simplify this. Again, you know, we can put this thing in this into the you know, this parenthesis, and that means we cancel all this. This one becomes p theta. Same thing. This one we cancel all this. This one becomes p theta. Okay, and we get like a z and the z 0.5 out of here. So the first term we have p theta minus 1. Okay, and then the second one, okay, we get this one out. We get this one out. So plus p of theta minus p of theta minus 1 plus p of theta minus p of theta plus 1. Okay, and then, okay, the last term we get plus p of theta plus 1. Okay, so well, this one cancel each other. This one cancel each other. So we are going to end up with 2 p of theta. So, you know, the result is going to be, you know, p of theta divided by z. Okay, you can try to, you know, put in all these. I mean, any of these 4 cases. Okay, and you are always going to end up with, you know, p of theta divided by z. What does that mean? What does that mean? Here, okay, we are trying to put, okay, you know, we put this w into as like the probability of the location where the the partition will be at each island. Okay, and it will give you, you see, at the ith turn, at well, rth turn actually, I mean, it's going to give you p of theta divided by z. So you see, originally, okay, you put p of theta divided by z as the probability where it is going to end up at the island theta. And at the end, it tells you that, okay, the probability for, I mean, after one iteration will stay the same, right? Regardless the relationship between different islands, I mean, the neighboring island, obviously, between the neighboring island. Okay, as long as your probability at each island look like, you know, that, okay, I mean, if you try to multiply this matrix, okay, meaning you try to, you know, expand for one more step, it's going to go back to the original term, right? That means what? That means no, you know, it's this means like this probability distribution, okay, remember the p, you know, p theta minus 1, p theta plus 1, blah, blah, blah. This basically means the population at each island, right? The population at each island. Or you can say it's like the posterior distribution value at each location, whatever you call it. Okay, and you know, why do we need to add a divided by z? Because we want to normalize it. The z is normalizing term, by the way. Okay, so this, okay, this okay, derivation basically tells us that this w, okay, or this probability distribution, okay, like this, is a stabilizing vector, okay, meaning v multiplied this matrix, let's call that matrix M, it's going to be v again, right? Okay, v, let me repeat, v times this matrix is going to be v again. So basically, it's stabilized, okay, meaning we know like no matter where we start, the distribution will diffuse and explore other locations. But, okay, we know, okay, there will be some stable state. There will be some stable, and we have shown that this target distribution, the target distribution is a stable state, right? Right? So, you know, so this is important. This tells you that, you know, it is very likely, okay, after repeatedly applying this matrix, okay, eventually you are going to end up with this target distribution, okay? But, okay, why, if you remember, I keep telling you guys that, okay, yeah, this is I would say it's a kind of an argument instead of a proof, right? I didn't say this is exactly a proof, right? Why am I saying that? Okay, because okay, we know, yeah, applying this matrix, you know, repeatedly is going to end up, I mean, it's likely going to end up at a stable state. Yeah, we know that. But we cannot be sure. We know target distribution is one stable state. Okay, as I already showed you, right? But we didn't show that there's only one stable state, right? You may have more than one stable state, right? So mathematically, this is not exactly a proof. This is just an argument to tell you that, okay, this diffusion process, okay, eventually, okay, it's going to end up at some stable state. And this target distribution happened to be one of the stable states. But, in all this derivation, I didn't show you there's only one such stable state. So I cannot say this is a proof, okay? But this is something I can give you that's closest to a proof. If you want to see a more, formal proof, okay, than this, okay, then remember I told you, okay, there's the Gurman's textbook that you can refer to, okay. That one, okay, will talk about this whole thing in a much more rigorous mathematics manner, okay. But in computer science, I hope like you guys is satisfied with this argument, okay. So this algorithm, okay, is best known as Metropolis algorithm, okay. Why is it called Metropolis algorithm? Okay, the Metropolis refers to the papers, the author of the paper that proposed this algorithm. Okay, actually the first author. His last name happened to be Metropolis. If you know like English, you will know Metropolis means like big city. Okay, but no. This in here, okay, this really just means somebody's name. Okay, it just happened to be. His name happened to be Metropolis, yeah, this has nothing to do. Okay, this algorithm has nothing to do with big city. Okay, and to be honest, okay. The reason, okay, to be the first author, okay, this guy to be a first author is really not because he's that good, okay, because it's really because his advisor is really good, okay. His advisor is actually the mastermind behind this algorithm, but he got lucky because he found a good advisor. When they published a paper, his advisor put him as the first author. Some advisor will put a student as first author, some advisor will not. If the result is significant, okay, some professors will prefer to put his own name as the first author. But it happens that this Metropolis, his advisor is very nice, so he put his students as to be the first author, and so he got lucky. Okay, so his name is recognized. As like a name of an algorithm. Okay, so it tells you that it's important to find a good advisor. Okay, yeah, just kidding. Yeah, okay, so yeah, so this whole derivation. Okay, well, it takes some time. So yeah, it's about time to take a 10 minutes break. When we come back, we are going to discuss like a more general Metropolis algorithm. Okay? Okay. 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 So Previously, we talked about this Metropolis algorithm, and we also show you like some arguments why it worked. Okay, but it turns out that we can generalize it. Okay, to make it more applicable to to a lot of cases, okay? Because in previous, like the partition example, we consider only simple case of discrete positions. Okay, we have like a chain of islands, right? And on one dimension, because it's one-dimensional islands. Okay, the islands are distributed in one dimension. Okay, and with moves that propose just one position left or right, we each time, okay, we flip a coin and decide to propose to move left or right, and then of course we need to determine whether or not we really move to that particular island, okay, based on the ratio of the populations, right? So this is the simple case, okay, but it turns out that we can generalize it, okay, in a much more realistic scenario, okay. It can be used for continuous values on any number of dimensions, and with more general proposal distributions. Okay, remember what the proposal distribution means, okay? The proposal distribution means like, where you can propose to move, as well as the probability, okay, distribution for your proposal, okay? In the previous simple case, the proposal distribution is so simple because you only have like a left or right, two cases, and also, each of them is 50% chance because it's a coin flip, right? So, but now, okay, it can be, much more complicated. Okay, it can be much more complicated. The proposal, can be drawn from the continuous space, and also the probability doesn't necessarily need to be, the same for each proposal. Okay, so first we have some target distribution, okay, P of theta, over a multi-dimensional continuous parameter space, from which we would like to generate representative sample values. So now, okay, this situation is much more similar to our posterior distribution case, okay, because the posterior distribution is a multi-dimensional continuous parameter space, okay? So we must be able to compute the value of P of theta for any candidate value of theta, okay, which is not a problem, okay, if you want the P of theta, not exactly P of theta, but like something that is proportional to P of theta, which is like the likelihood times the prior, right? Okay, the distribution P of theta does not have to be normalized, okay, because we only want something that is proportional to that, okay? In typical applications, P of theta is the unnormalized posterior distribution on theta. So it's a product of likelihood and the prior, as I already mentioned, okay? So sample values from the target distribution are generated by taking a random walk through the parameter space. So it's still a random walk, okay? And the walk starts at some arbitrary point okay, specified by the user. Okay, just like the partition, okay, we can start the position of the partition from island 1, island 2, island 3, island 4 to island 7. It doesn't matter, okay, because it's a random walk. Eventually, the partition will move to move more often to the places, to the islands with more populations. Okay, eventually. Okay, so the starting point should be some place where P of theta is non-zero. Why do we have this constraint? Because remember, okay, no matter what, it's a special case, the simple Metropolis algorithm or the general Metropolis algorithm. Okay, at the end, when you decide to accept the proposed move, okay, or not, you are going to end up, checking this, where is it? This value, right? The P move is going to be mean of P theta proposed divided by P theta current, or 1, right? It's the smaller one of these two terms. So if your P theta current is 0, we have an issue, right? We have an issue. So this term, the initial location of this, the P theta of the initial location has to be non-zero. Okay, but it's normally not an issue. Normally, okay, if it's really going to be an issue, you can certainly start from another initial location again. Okay, if you found that, okay, this place it doesn't lead you to go anywhere, most likely you have this initialization issue. You can change the initial location. That's pretty easy, and you don't need to worry about, once you get a good start, you don't need to worry about that you are going to go to some place that have with the P0 P theta to be 0. Why? Because if the P theta proposed is 0, you can never go there, right? Because the probability of moving there is going to be, this term is going to be simply 0, right? So you don't need to worry about if you have a good start, whether or not, after you move several steps, it's going to go to a place where the P theta is 0. This is impossible. Okay, according to the Metropolis algorithm, okay, this P move is definitely there. Okay, actually, it's this P move, okay, that's guaranteed the result is going to converge to the target distribution. Okay, you can see that the proposal distribution, okay, what the proposal distribution impact is how quickly the sampling process converge to target distribution, but it doesn't really create a problem of the conversion. Okay, so come back to, okay, so this random walk progresses at each time step by proposing a move to a new position in parameter space and then deciding whether or not to accept the proposed move. Okay, this proposal distribution can take on many different forms, okay, with the goal being to use the proposal distribution that efficiently explores the regions of the parameter space where p theta has most of its mass. So the proposal distribution can be different, okay? I mean, you can see in the discrete partition case, it's just like left and the right, right? I mean, and with 50-50% chance. I mean, that's so simple. But in a continuous high dimensional case, what do we do? Okay, we just need to make sure a proposal distribution for that we are going to use for proposal. I mean, it's going to have a quick way to generate random values. Okay, I mean, so pretty much like any distribution, any reasonable distribution, you know, it should be good enough. Okay, but for our purposes, okay, we can consider a generic case in which the proposal distribution is normal, centered at the current position. Okay, I mean, we know that a normal distribution or Gaussian distribution can be generalized to high dimensional, right? I show you guys like the two-dimensional Gaussian, right? Okay, and for n-dimensional Gaussian, it's pretty much just straightforward extension of like the second dimension, two-dimensional Gaussian. Okay, so it's, I mean, we know that Gaussian distribution is simple, it's easy to draw, you know, random value from. Okay, so I'm not saying you have to use Gaussian distribution for the proposal distribution. I'm not saying that. I'm saying it's a easy, it's a good candidate. Okay, it's just a good candidate. Okay, so the rest, okay, talks about like that you know, using like a Bernoulli likelihood and beta prior. I mean, for like the you know, the coin flips. Okay, because you can use that to use coin flip to justify the generalized Match-Paris algorithm, but you know, I will skip that. Okay, this set of slides, okay, because as I said, this set of slides comes from the Doing Bayesian Data Analysis book. Okay, so some of them are useful, but some of them I think like we already talked about, so I will skip that. Okay, so this so okay, but this slide is important. So representative parameter values can be so this is the why Match-Paris algorithm is so important. It's, I mean, why it is, you know, it is designed. I mean, it's considered like a very, very good. Okay, so representative parameter values can be randomly sampled from complicated posterior distributions without solving the integral in Bayes' rule. Okay, remember like the denominator, the P of D, okay, is the term that we need like to do the integral, and that's the difficult part. Okay, that's the difficult part. I mean, when it comes to like analytical like a solution. Okay, if you want to get a closed form of the posterior distribution, I mean, a lot of time you will end up like you know, having trouble with like that P of theta, P of D, okay, P of D. Okay, so by using only simple proposal distribution for which efficient random number generators already exist. Okay, so we don't need to use that. I mean, we don't need to do the integral. Okay, instead we just use a proposal distribution to explore the space and to use like the p move. Okay, to determine like whether or not to move to that place. Okay, by doing so, like eventually you are going to generate like samples that that can be used to describe the posterior distribution. The more important thing is, okay, always need to decide whether to accept a proposed parameter value is the mathematical formulas for the likelihood function and the prior distribution. And these formulas can be directly evaluated from their definitions. Okay, so those things are easily evaluated. Okay, so you may wonder like how. So yeah, this is a sampling process. So why is sampling more effective than the grid approach? Okay, you say grid approach, we just find the value, okay, at the grid points, and then you approximate the posterior by finding those values, and the integral will become like adding all those values and use that as denominator. Okay, so it doesn't look like it's going to be an issue. Okay, and it looks like a grid approach. Looks like it's also efficient. So why sampling technique is more efficient? It is because, okay, in the sampling, this metropolis sampling process, you can see that it's going to jump. It's going to jump to the places with a higher p theta value, right? It tends to jump to those places with higher p theta values because of the p move, how the p move probability is calculated, right? Okay, if that place has a higher p theta value, it's more likely we accept that proposal, right? So it means that, okay, we are going to naturally stay at the places where the probability mass is larger. We will naturally stay at those in those areas. But for the grid approach, we treat each point with the equal probability, right? Each grid point has the same we just treat them the same, right? So if you use the grid approach, you will find which is most. Actually, it's always the case. I can probably say that. Okay, like a lot of distribution only has values at some location in the distribution in the parameter space. Okay, very small when it's only a very small region, that distribution has value. And in all the other parameter space, okay, even though in a high dimensional parameter space, the parameter space can be very, very huge, right? But in maybe 99% or even higher than that, okay, percentage of the distribution, the parameter space, okay, that you pretty much always get like some value very, very close to zero. Okay, so using the grid approach in such a case really doesn't help. You are going to just waste your time, okay, if you use grid approach, because you should just treat those places, you just, because if those areas is has a zero value, you don't even need to bother sampling at those in those areas, right? Okay, so, but if you use grid approach, yeah, I mean, you are going to end up like calculating value from those areas. Okay, but if you use this type of random walk approach, yeah, its mechanism, automatically, forbidden you to move to those areas. Okay, because if the p theta is close to zero, you just don't go there. It's impossible for the proposal to be accepted, right? Okay, because the proposal distribution, how the proposal distribution is determined to be accepted or not. Okay, how we decide it is accepted. Well, we will naturally, the random walk will naturally, sample more in the area that we have higher value in p theta. And it will naturally stay, almost, it will naturally spend almost no time in the area where the p theta is close to zero. Okay, so this is very, very important. Okay. So yeah, I mean, there are other sampling techniques. That book talked about Gibbs sampling, but I think just like in our book, we use another sampling technique. These are all like a variation of the Metropolis algorithm. Okay, so I will skip this because I think like these are not the target. Okay, I mean, there are so many sampling techniques out there nowadays. Okay, after the Metropolis algorithm was proposed, okay, this like 20, 30 years, I mean, has the Bayesian data analysis field, because it has become so popular. Like a lot of mathematicians and the statisticians spend time developing like sampling techniques. Okay, but so I don't think we will we'll move to this one. Okay. So remember, like when you prepare your final exam, I'm not sure if this is this slide like in your PDF file. No? Okay, I'll update this. Okay, I mean, because I think like I cut like the previous PDF file short. Okay, so I didn't include this some of the rest of discussion. Okay, in the handout that I have the TA upload to the E class. So I will update the slide. I mean the handout. Okay, in the E class. But keep in mind, I will not cover everything in this set of slides, okay, in the final exam. I will only cover what I talked about in class, okay, in the final exam, okay? So any simulation that samples a lot of random values from a distribution is called Monte Carlo simulation. I told you guys Monte Carlo refers to the random process, right? Okay, so Metropolis algorithm and Gibbs sampling, all the sampling techniques are specific types of Monte Carlo process, okay? Because they involve, they are, in nature a random process. Okay, the random walk is a random process. So any process in which each step has no memory for states before the current one is called a Markov process. Okay, and a succession of such steps is a Markov chain, okay? Because remember, like in the Mitch-Paris algorithm, okay, you move, okay? Let me use the simple case of the Mitch-Paris algorithm. You see, like the partition move, okay, to either the left side or right side of its island, right? Okay, so he does not move to all the island, okay, in the next step. He can only move to the nearby islands from the current island that he's located, right? Okay, so that's what I meant by, okay, each step has more memory for states before the current one. Okay, say if the partition initially at island 1, okay, after a couple of movements, he moved to island 4. The next step, he can only move to island 3, island 5, or stay at island 4, right? Okay, and it has nothing to do with whether or not few steps earlier he was at island 1. It has nothing to do with that, right? Okay, the only thing that is going to affect his next move is the location, the current location of this partition, right? Okay, so that's what I meant by it's a Markov process. Okay, only each step is only affected by the previous one. That's it. Okay, not the like 2 steps before or something like that. Okay, so a succession of such steps, or like the whole random walk, okay, can be considered as a Markov chain. Okay. So there are 3 main goals in generating MCMC sample from posterior. Okay. First, the values in the chain must be representative of the posterior distribution. Okay. So they should not be undoubtedly influenced by the arbitrary initial value of the chain. Okay. And they should fully explore the range of the posterior distribution without getting stuck. So this has 2 important meaning. The first one is the initial location should not have impact to the result. Okay, if the initial location has impact to the result, that means your chain is not representative enough to the posterior distribution. Okay, and also, okay, your chain, okay, should fully explore the range of the posterior distribution. In other words, the proposal distribution needs to be able to, explore the whole posterior region where the p theta has non-zero value. Okay, so obviously this has something to do with how effective is your sampling technique. Okay, so different sampling technique. For example, like in this book, the Mitch-Paris algorithm, the Gibbs sampling is much more effective. Of course, different sampling techniques, has also different assumptions. Okay, I don't expect you guys to understand all the sampling techniques in detail. That's just impossible. Okay, I mean, but I expect you guys to understand, for example, like the basic the idea of sampling technique, at least like the Metropolis algorithm. You need to understand why, how it is like, you know, what it is, and you know, at least you know the argument, why it is correct, okay? So second, the change should be sufficient size, should be large enough, okay, so that estimates are accurate and stable. Okay, so here, okay, the size of the chain, okay, again, has something to do with the sampling process. Okay, if your sampling process is more efficient, then you don't need that many samples. Okay, you probably need like just a couple of thousand. Remember, like in the previous like examples in the textbook, we used like only like 2,000, right? Normally, we only generate 2,000 samples, and the result is already pretty nice. That's because, if I remember, we use PUA sampling technique, and that sampling technique is very powerful. Okay, but if you use like, for example, even for general Metropolis algorithm, okay, it is really not that powerful because, well, you can obviously imagine that was the first sampling technique that was proposed. Obviously, after so many years, there are many sampling techniques that have been proposed to improve Metropolis algorithm. Okay, so yeah, so in doing Bayesian data analysis, I mean, we usually normally just generate like tens of thousands, about 10,000, okay, to even like 20,000 samples, okay, for each chain, okay. But again, that depends on which type of sampling technique we are using, okay. So the change should be the change should be generated efficiently with as few steps as possible, so not to exceed our patience or computing power. Okay, but nowadays, okay, because the computer has become so powerful, okay, this is normally not going to be an issue. Okay, if you try to generate, for example, like 2,000 samples by using like the example in the textbook, okay, you will find that, yeah, it takes some time, but just a couple of seconds, okay, really is not going to be an issue. Okay, that's because the current personal computer is so powerful. It was so powerful. I mean, back to like, remember like this sampling technique was like first proposed like in the early 90s. At that time, the computer, the computing power of the like early 90 computer is actually weaker than most of the smartphone that you have in your pocket. Okay, so yeah, I mean, obviously there's like you know, we need to take into account the computing power, but this is normally not the issue. I mean, for the current computer technology. Okay, so if you want to know how representativeness, like the MCMC chain that you generate, okay, so you can use visual examination of the trajectory, and also you can consider certain numerical description of the convergence. Okay, the reason I want to cover this part is just to show you, I mean, some of those things. I mean, so first, a visual examination, okay, when you generate samples by using like MCMC, any of the MCMC sampling techniques, okay, first let me repeat, okay, this is like a, this is for a different textbook, so they use like a different way to generate like a different sampling technique and to generate the result. And this is like based on R. So I to our if you remember like our Python like textbook, okay, we only has like the upper left figure and the lower right figure. You may not think like upper left figure. You say, oh, upper left figure doesn't look like we have that that one. But if I show you another one, it should be more obvious to you, right? The upper left figure. You remember like in the textbook, I mean every time we generate like a posterior, we have something similar to upper left figure, right? That shows the trajectory of the parameter value. Okay, so you see, it actually represents like how the sample, the parameters are jumping from one value to another. Okay, remember it's a random walk, right? So it goes up and down. Okay, it goes up and down. So, but you may wonder like how come, this one doesn't look like you can see there are three chains, right? There are three chains in the upper left figure, right? But you feel like, well, this upper left figure, these three chains do not mix so well like this one, right? So why? It was because, take a look at the iteration. This is like the first 500 iterations. Okay, so in the first 500 iterations, you can see these three chains actually initialized at the different locations, right? And they just got started, so they gradually converge to the area that has higher posterior value, okay, which is like somewhere close to 0.8, right? But you can see, before like 400, 500 iterations, these three chains, they are still very far apart from each other, right? And that's nature. And think about that. Remember when we draw our result that looks like this, we actually, if I remember, I told you we got rid of the first 500 iterations, right? We use those first 500 iterations to tune our, sampling process, right? Why do we need to tune it? It's because if you don't get rid of those earlier sampling process, they are going to be affected by the initial value, okay? And so the upper left corner indicates that the parameter value, okay, or the trajectory of of different chains, okay. If your chains are representative, most likely these different chains, even though they start from different locations, they will mix very well. Okay, they will mix very well, and if you still remember, in the Python version, okay, we have upper left figure and the lower right figure. The lower right figure is the kernel function, okay, basically. I mean, it's kind of like if you try to look at this figure, okay, in a turn 90 degree, you turn this figure 90 degree and calculate like how many the frequency of each values from 0 to 1, okay, and the one with the more frequent visit, okay, will has a higher value, something like this. Okay, so you create a kernel function like this. Okay, so we have these two, but we didn't have the lower left, this shrink factor, and we didn't have this autocorrelation. Okay, for the so the upper left one and the lower right one, I mean, should be relatively easy for you guys to understand. For lower left one, it is a special, it's called German factor, okay, or shrink factor, okay. Basically, okay, we are looking at, I mean, if this value is reduced to close to 1, okay, that means like your chain is generating very well, okay, but since this derivation takes some mathematical skill, okay, so we'll skip that, and even doing Bayesian data analysis, they just say, oh, this has to be close to 1, okay. If it's larger than 1.1, you have an issue. But just that, okay. It didn't actually talk more about this, okay. So I will skip this part. But the upper right one, I would like to spend some time to talk about it, okay. Because like the upper right one, okay, the correlation, okay, has something to do with the effective sample size. Remember, in our like summary, parameter summary, we show like for example, like after we generate like a posterior for some parameters, we show like maybe like the average. Mean. We show the mean, we show the standard deviation, and we show like maybe 94% HPD, the range, right? And we have a field that tells you effective sample size, right? I told you guys like don't worry about that, okay? We will talk about that later. So that's now is the time that I would like to talk about that. But before we talk about that, that's equivalent to this ESS. Okay, so this ESS has something to do with autocorrelation. Okay, so I will have to tell you guys what the autocorrelation is in order to tell you what the ESS is. Okay, so well it's so I will skip this. Yeah, this one talks about like the figure on the lower left corner, so I would skip that. Okay, and yeah, autocorrelation. The autocorrelation is a measure of clumpiness. Okay, it's simply the correlation of the chain values with the chain values k steps ahead. Okay, so there's a different autocorrelation for each choice of k. So autocorrelation, okay, if you look at this lag represent that k value. Okay, this lag represent the k value. So what does that mean? Okay, let me show you this figure. Yeah, maybe it's let's take 10 minutes break. When we come back, we will discuss this autocorrelation. Okay. Yeah. Okay. Okay, let's get started. Okay. Yeah, I was looking at the NBA games. I mean, do you guys like watch NBA games? No? Okay. Yeah, I mean, I don't do much exercise, but I love watching like a lot of different sports games. Like, for example, NBA games. Like today, Lakers is playing with like Golden State Warriors. I think like it's interesting to see like LeBron James and Steve Curry playing each other. I think like probably you don't see that anymore. Like in the future, maybe next year, I think LeBron James will retire. Okay, so this is perhaps his last dance. Okay, yeah. So well, anyway, yeah. So come back to this autocorrelation. So first, like, what does that mean? Autocorrelation. Okay. You guys know like what the auto means here. Okay. I mean, for example, like auto, you see a lot of English words that start with auto, right? For example, like automobile, like anything else? Automatic. Okay. The prefix auto, okay, actually stands for self. Okay, self. Okay. So for example, like automatic. Okay. Matic is like a mechanism, kinetic. Okay, so self mechanism. So it's you do something like something happen like by itself. Okay, and automobile. Okay, same thing. Mobile is something that move, right? So automobile, self move. So like the car can move by itself, right? So auto actually is a prefix that stands for self. So autocorrelation is self-correlation. Okay? You guys know correlation, right? Correlation is not a new term, right? The autocorrelation is new, but I mean, once you know the auto means self, the autocorrelation should not be too difficult to understand by you guys. Okay? So given a series, given a time series data, okay, you can compute the autocorrelation by something like this. Okay, so for example, you see there's here we have a time series data. Okay, and this ACF means autocorrelation. Okay, this 1 means k equal to 1. Remember like a previous essay, like you can compare, okay, with the itself, okay, with the chain values, k step ahead. Okay, so this k is is the what appear in the parentheses. Okay, so this 1, it just means like you move this chain 1 step to the right. Sorry, it should be 1 step to the left because you look ahead. Okay, 1 step to the left. Okay, and then, okay, you try to, because you move, if it's like let me draw something that's more dramatic, okay? Say if you have something like this, you move this thing one step to the left, what you are going to get is something like this, right? Right? So for each x value, you now has 2 points, right? You have this point and this point, right? Right? For each given x value, you have 2 points, right? Because you have 2 points at each given value, you are able to compute their correlations. I mean, if you want to calculate correlation, you need to have 2 values, right? So you are calculating the correlation of the y of these 2 sets of y values. Okay, for every every x value. Okay, so this is like if you move this one step to the left, then your k value is 1, and then for example in this example, your ACF1 is 0.96. If you remember like how we calculate correlation, 0.96 is quite high, right? Okay, the correlation normally is in between -1 to +1, right? If something is higher than 0.9, that's already very, very high correlation. So this is 0.96. That's darn high correlation there. Okay, but you can obviously imagine if it's a time series, when you increase the k, in other words, if you try to move this chain more to the left and then calculate the correlation, when you increase the k, the correlation will reduce, right? The correlation will naturally reduce. So you can see when k is when k is 5, it reduced, the correlation reduced from 0.96 to 0.75, right? And if you move like 10 steps ahead, the correlation reduced to 0.55. Okay, so this lag, as I said, this represents the value of k. Okay, and you will naturally see such a decrease of the autocorrelation. Okay, so what does autocorrelation stand for? It stands for like how much dependency this time series data has. Okay, from the previous location to the next one. Okay, so for example, if I'm here, okay, for this current step, if I move next, we know like because it's a Markov chain, right? It's a Markov process. So the current step influence where you are at for the next step. That's nature, right? That's nature. But if the k is larger than 1, the autocorrelation value should reduce quickly, right? Should reduce quickly. If it's a good Markov chain, okay, if it's a good Markov chain, then it should only dependent to the previous step, not to the step like more than one step in the past, right? The lower the value of the autocorrelation indicates that the more information you can draw from this time series data. No, information theory wise. Okay, information theory wise. So the autocorrelation can be computed for any lag of interest. But for our applications, okay, we typically interest in lags from around 1 to 20 also, okay, because if the K value is too big, as I said, like, it reduces quickly, right? If you already consider, I'm sorry, if you already consider like K to be higher than 20, like, I mean, pretty much all kinds of time series data will have very low autocorrelation anyway. Okay, so it doesn't, we only consider from 1 to 20. Okay, something like this. Okay, so you can see, for example, this one, okay, we care more from here to here. For something like lags that are larger than 20, obviously it reduces naturally, but we don't care that much. Not to mention this one, okay, this is also autocorrelation, so up to 20. So you can see that, okay, if you ask me, for example, okay, remember I told you, like, you know, for representativeness, okay, there are two ways to decide how representative, like, representativeness your chain has. Like one is like the upper left figure that shows like if your chains mix well or not. I mean, if you look at this one, it looks to us that it mixes pretty well. I mean, if you only look at the upper left one, I mean, to be honest, I mean, it's, you know, if you look at this, I mean, more carefully, you will still feel like they don't mix so well. But it's hard to say, right? Because it's a visual result. So visual inspection is easily misleading because of the, you know, it's more subjective. Okay, so probably some people think, oh, this is like this mix pretty well. The chains are mixed pretty well. Some people will think, some students will say, oh, this looks like it's I mean, still they do not mix so well. Because if it's like this, obviously they don't mix well, right? This one is obvious. I mean, nobody will say they mix well. But this one is hard to say, right? Some people may say, yes, they mix very well. Some people will say, well, they don't mix so well, okay? So sometimes it's hard to say, okay? I mean, but the other clue is to look at the statistical values. For example, like autocorrelation. Okay, you can obviously see that, you know, even at around 20, okay, the autocorrelation for these chains are still higher than 0.4, right? So it doesn't really, it's really not that good. Okay, you are looking at the autocorrelation that's like much lower than 0.4 when your lag is 20. You should see this one reduce, okay, I mean, become very low very quickly. Okay, if it's not a case, then it just represents your chains are not mixing very well. Okay, or the chains are not representative enough to your posterior distribution. Okay, and so yeah, Okay. So we would like to, some measure of how much independent information there is in autocorrelated chains. In particular, we can ask what would be the sample size of a completely non-autocorrelated chain that yielded the same information. This is like the definition of the effective, how we define the effective sample size, the ESS. It's defined as N. This N represents like the number of samples that you draw from. Maybe for example, like we draw 2,000, right? Okay, but in a different textbook we draw like 10,000. But you get an idea that N represents like a number of samples, like you draw, or by using the sampling algorithm. Okay, you can obviously set it like by yourself. But this N is divided by this parenthesis 1 plus 2 times summation k equal to 1 to infinite ACFK. Okay, first, because this autocorrelation is almost guaranteed to be greater than 0. Okay, so this value is not likely to be negative. Okay, so you can imagine this 1 plus something. This denominator, this is greater or equal to 1, right? Okay, so in other words, like your N, okay, even though you draw like say like 10,000, maybe at the end the effective sample size is not going to be that high. Okay, if you want your chains to be representative, you make sure this ESS value is large enough. Okay, not the number, not this N, okay, but the ESS value. Okay, but as I said, the better the sampling algorithm that you use, the more likely this value will be smaller. Okay, and you may say, well, this is k from 1 to infinite. How can we calculate that value? Because, well, this is an infinite series. And it looks like it's difficult to calculate, right? But in practice, this infinite sum, okay, you don't need to calculate like from k to 1 equal to 1 to infinity. As long as you get a term, okay, that is or smaller than 0.05, you can stop. Because it should be, when you stop at this value, okay, you add like from k equal to 1 to this k value that makes this ACFK smaller than 0.05. This summation should be representative enough for you to calculate this ESS. Okay, so come back to this one. Look at here, ESS equal to 605.8. It was indicated at the upper right corner of the upper right figure, the ESS. So this one actually, how many samples did we draw? Okay, we actually, the first 500 is used for tuning. So we actually, did not account for the first 500. But we, from 501 to 10,000, we actually, each chain has, 9,500, right? So it's pretty long chain, right? But such a long chain, their ESS is only 605. That's due to the fact that we have a relatively high autocorrelation. Okay, in other words, like this chain, okay, they didn't provide like enough independent information in the chain. Okay, that, as I said, this is affected by mostly the sampling technique. And because this example, we use like a Metropolis algorithm. So Metropolis algorithm, as I say, is like the first algorithm like in this sampling technique. Okay, so it is a relatively simple, naive sampling technique. That's why, okay, it's not very effective, as you can see. Okay, yeah, I mean, for the other type of sampling technique, for example, like Gibbs, or like the one that we use, I mean, for our textbook, okay, they are more advanced sampling techniques. So normally the number of samples you draw will be closer to the ESS value. Okay, so for example, sometimes you may even see like you know, this ESS value to be larger than n. Why is that? It's because like you know, yeah, it's not impossible. You sometimes can find that, can see that. I mean, where is it? Okay, because you can remember like it's defined something like this, right? So I mean, it's autocorrelation, right? So correlation could be negative, right? It could be negative, but most of the time it's positive. I mean, when it comes to autocorrelation, but it doesn't guarantee it could, I mean, it's not negative. So yeah, I mean when the SAFK is negative, I mean it could impact the ESS to be larger than the number of samples. It's possible, but not very likely. Okay, not very likely. I mean, let me go back to let me, sorry. I just want to show you the, yeah. Yeah. So this, the reason, you see, we have this kernel function, okay, and this you know, the chain, okay. So this one is the upper left corner figure. This one is the lower right figure. I mean, yeah, I mean these two figures are the most important ones. I mean, and what I was trying to tell you is this one. Okay, this EFFN is the effective sample size. And remember how many samples did we draw? I mean, I just arbitrarily pick this one, okay? So this one is like, where is it? Where they show, well, we didn't, shoot. Oh yeah, here. you can see it's about 1,000, right? We draw like about 1,000 samples, right? Okay, and so it's, you know, it's quite effective, right? I mean, close to 1,000. I'm not saying that it's 1,000, okay, but it's close enough, right? I mean, it's the effective sample size is like more than 80% of the sample, right? So it's pretty nice. It's pretty nice already, and that's because like the sampling tech algorithm that was used in our textbook. Let me use another example. So this one we draw like 2,000 samples, right? And do we have this? Yeah, you can see sometimes it can even be larger than 2,000. Not very likely, but sometimes it happens, especially in some simple cases. Because this is like, remember this case is very simple. We only have one outlier, something like that. If you still remember the case, this example. So the reason, okay, I want to talk about this part is to talk about, you know, because at that time we, you know, the mean standard deviation, the MC error. This one is like you don't need to worry about that. This is for like Markov chain error, okay? But these two fields are pretty much easy to understand, okay? It just represent like the range of your 94% HPD. But this one is important because it tells you like how representative your chain is, okay? So there are so many of these like well, yeah, you can find, I mean, a lot of this. This one we generate 2,000 samples, and the result. Do we have the result? Well, we didn't put the summary here. Right here. Yeah, we generate 2,000, but this one. Yeah, this one is, yeah, it's because of the relatively simple case. I mean, because this case was generated by us, but a lot, I mean, of this is also due to like the effectiveness of the sampling techniques, okay? So I just want to tell you the meaning of that field, okay? So, oops, shoot. Yeah. So ESS, okay. So each chain, okay, basically, I mean, has like a 9,500, n equal to 9,500. So yielding like a, oh, I forgot to mention, yeah, this is actually like a, you have to add them up. So, so because we have like multiple chains. So 9,500, so total will be 28,500. But the autocorrelation is high, so that ESS is only 605. Okay, so same thing apply for the previous ones. Okay, I forgot to add them up. No wonder it's like easily over like 2,000. Yeah, because in a textbook example, we have like 3 chains, right? So 2,000 actually end up having like 6,000 samples. So 6,000 samples, I mean, remember like we saw like ESS to be like 5,000 something, right? So that's like reasonable, okay? So how big should the ESS be for accurate and stable? Oh, by the way, I forgot to mention, okay? So if you want the higher ESS, okay, you want the higher ESS, the higher the ESS, the better, the more accurate and the stable picture of the posterior distribution you can obtain. Okay, so how high do you need? Okay, if you want to have like a very good estimate of the 95% HDI, this book suggests like a 10,000 ESS. Okay, this is ESS, not like the N. Okay, it's like the number of effective sample size should be 10,000. But if you look at like the textbook that we have, okay, they only use 2,000 most of the time. 2,000 is equivalent because we have 3 chains, right? So it's 6,000. Okay, the reason the author of the textbook thinks this is good enough is because the textbook, the PyMC3, package, in the PyMC3 package, the sampling algorithm is more advanced, okay, than the one that was used in this package. Okay, so but still, like 6,000, you normally end up having like around like 5,000 effective sample size. It should be relatively okay. Okay, but some people will think, okay, you probably need a higher ESS. Okay, maybe twice of like 5,000, so it makes like 10,000. But the more important thing is you look at this ESS value, okay, and you look at some of those statistics, okay. If those statistics are more looks good, I mean you normally can accept that. And also, okay, as I said, like you want the higher ESS, right? So how to increase the ESS? The easiest way is you just increase the N, right? I mean, if like 2,000 is not enough, you can obviously set it to 5,000, okay? And as I said, like for the current computer, like hardware, setting the sample size to be 5,000 or even 10,000 is not going to be an issue. You just wait for another couple of seconds, okay? It shouldn't be more than a minute, and you can get a pretty good estimate of the posterior distribution. So this is obviously one way to do it. Another way to do it, obviously, is to use a better sampling technique. Okay, and a lot of this like package, because they already have this, remember, I mean, in the PyMC3, I mean, you have those 500 steps as a burn-in period, right? And those burn-in periods actually help the package to determine the best sampling technique automatically for you. So they normally will use the best sampling technique for you. Okay, so you normally don't need to determine the best sampling algorithm by yourself. Okay, I'm not saying you cannot tune it by yourself. Okay, you can still tune it by yourself, but I'm saying like a lot of this package now make this tuning automatic. Okay, so you can rely on this mechanism. Okay, you don't need to worry about this thing. Okay. Okay, so I just want to point out this. Okay, ESS. Okay, which is important concept, but well, we have like a. So this is pretty much the other part. Okay, another thing I want to tell you. Okay, but I'm running. I don't want to cover that material because that's a little bit too much. But remember, I told you some sampling techniques tend to have problems when your parameters are highly correlated. If you remember, we intentionally create such an example by generating like x1 and x2. We intentionally to make them highly correlated. Okay, and then I told you okay, the sampling process may be affected because of these parameters are highly correlated. So you may ask, so which type of sampling techniques could be affected by the highly correlated parameters? Okay, for example, the Gibbs sampler. Okay, I don't think I will cover this one. Okay, for this class, but I just want to point out there are some sampling techniques that may have such a problem. Okay, so yeah, this is one of the example. Okay, that could have this issue. Okay, when your parameters are highly correlated. Okay, so yeah, so I think because obviously Gibbs sampling is a lot of stuff to cover. I think I will skip that. Because to be honest, even the Gibbs sampling is no longer considered advanced. Okay, the one that I used, in the PyMC3 is much better than what the Gibbs sampling. The Gibbs sampling, the reason to talk about Gibbs sampling in the previous textbook, one of the reasons is because Gibbs sampling is kind of related to Metropolis algorithm. So it's easier to understand. Okay, but Gibbs sampling is a kind of special sampling technique. Each time it sample one dimension. Because you see, in a higher dimension parameter space, normally you just use a high n-dimensional Gaussian distribution, right, to decide a proposal distribution, right? So in some sense, you can jump from when you jump, you change not only one parameter, you change all the parameters, right? That's a Metropolis algorithm is doing. But for Gibbs sampling, okay, it's every time you just jump, you just change one dimension. The other dimension value remains the same. So it's a very special sampling technique. Okay, but it's relatively easy to understand. And its mathematics can be derived. So that's why, okay, the other textbook cover that. But as I say, this is no longer considered the most advanced one anyway. Okay, so yeah, I think I will stop. Okay, just right here because the other part of the of these slides are not really that useful to our class anyway. So yeah, it also talk about the impact of smaller ESS, but I think you don't need to worry about that. Okay, this is also, remember another field, Monte Carlo standard error. Okay, this is also something you can consider. Okay, Where is it? This is MC arrow, this one. Okay, but most of the time this arrow is not going to be an issue. Okay, but if you are interested, I mean, you can check out the meaning of this field. Okay, in oops, sorry. Where am I? In this one. Okay. So I think that's about it for today. We'll stop it here, okay? Next time we will start from the generalized linear model, which is like I considered, okay, that let me see. Next time, how many lectures do we still have? 1, 2. We have, because the week after next I will be out of country, right? Is that right? I mean, I'll be out of town, out of country on the 16th, May 16th. So today is May 3rd. So May 16th, yeah, it will be next week, right? So next week we'll have class. The next week, I mean, we don't have class. And then after I come back, we'll have one more lecture, right? 1 or 2. Yeah, one more, I believe. Let me check. Oops, here. It's next week, and the week after next is I'm going out of country, and then yeah, after I come back, we have 2 more lectures. Okay, one for the 24th, one for the 31st. Okay, and then when we have the final exam, and then the presentation of the term project. Okay, so let me remind you once more. Okay, the final exam will be on the June 7th. I'm sorry, June 7th, and June 14th will be the project presentation. Okay, so we have 3 lectures. I will see, you know, what I can do about it, because like I'm not sure if I can talk about like model comparison, because like I probably need more than that amount of time. But anyway, okay, we should definitely have enough time to talk about generalized linear model. But as for like whether or not we are able to finish one more chapter, I mean, let's see what I can do. Okay, yeah, and I will make sure to upload the sample final, okay, to the E class for you guys before I go out of town, out of country. Okay. So any question? If no question, that's it for today. Okay. Thank you very much.